Now we have introduced here the strain rate along the x direction, y direction and z direction, that is given as epsilon dot x is as del u by del x, epsilon dot y as del v by del y, and epsilon dot z as del w by del z. Now we'll consider here a rate of volumetric dilation. Now recall here in Hooke's law, that is in machine design, if we apply the forces on the rod or a wire, in that case we observe that the length of the wire or the rod or the beam will going to increase in the direction in we apply the force, and because of the Poisson ratio other two dimensions will going to decrease. Solid objects such as wires, rods and beam stretch when pulled, then the object stretches in one direction, that is in the direction of application of a force, and it usually shrinks in the directions normal to that direction. That ratio of a change in a lateral strain to linear strain is called as Poisson ratio. The same is true in the case of fluid element. If the flow is incompressible, then the net volume of the fluid element must remain constant. Thus, if the fluid element stretches in one direction, it must shrink by an appropriate amount in other direction to compensate it. Then only the total volume change will be equal to 0. The volume of a compressible fluid element, however, may increase or decrease as its density increases or decreases respectively. This rate of change of volume per unit volume is called as volumetric dilation. Rate of change of volume per unit volume is called as volumetric strain in the machine design, and the same term is called as volumetric dilation in a fluid mechanics or a bulk strain rate. This kinematic property is defined as positive when the volume increases. However, for an incompressible fluid, the volumetric dilation rate is 0, since the element volume cannot change without the change in density. In the case of incompressible fluid, the density remains constant, and therefore, since the mass has to be remain constant, the volume change must be equal to 0. Now here we'll develop the equation for rate of dilation. The volumetric dilation is defined as a rate of change of volume per unit volume. Rate means we have ddt. Rate means ddt. Rate here dv represents the original volume of the element. So if the fluid element here has a dimension of dx, dy, dz, then the product of dx, dy, dz represents the original volume, and we represent here delta V as change in volume, which can be calculated on the basis of the shear strain along the x direction, y direction and z direction. So according to the definition of volumetric dilation, it's a rate of change of volume that equal to delta V per unit volume that equal to dV. So this one is delta is a change in volume and dV is the original volume. So it is given as 1 by original volume, and you have to take the derivative with respect to time, that is ddt of change in volume. So you are required to find out here change in volume. Let's consider here a two-dimensional figure of a fluid element having the original dimension equal to dx and dy, and dz is perpendicular to the board. Consider that the element is subjected to only the velocity along the x direction. So only the x direction will be changed this time, and this change in the x dimension can be visualized by this extra rectangle that you can see. So volume has been changed here. Initial dimension is dx, dy, and now new dimension is dx plus change along the x direction, which can be obtained as del u by del x into the velocity gradient along the x direction multiplied by dx in a small interval of time equal to delta t. So if you observe only the change due to the component of velocity u, in that case we can calculate volumetric dilation due to effect of u only. So in this case the original volume will be equal to dV, that equal to the product of dx, dy, dz, and this portion here represents the change in volume, and this hatch portion here represents the change in volume. So that equal to delta V, which is the product of this dimension, which is del u by delta x into dx into delta t multiplied by, since the effect is only due to u, the dimension dy and dz will not change. So multiplied by dy multiplied by dz. This one is change in volume. Now we'll put this and we can find out the volumetric dilation due to u only. So volumetric dilation due to the u component by this definition is 1 by dv, which is same as dx dy dz. So we have 1 upon dx into dy into dz, and you have to take the derivative with respect to t of change in volume. Change in volume is del u by del x into dx into dy into dz into delta t. So this time dx dy dz they are get cancelled here, and derivative of dt with respect to dt is taken as 1. So we have volumetric dilation due to the u component is del u by del x. If this fluid element is subjected to all the three components of velocity u, v, w, then we can calculate the total volumetric dilation. So that is the simply sum of the partial derivative of u with respect to x plus we have, if we derive this for v direction, that is the y direction, you will get del v by del y, and along z direction we will get del w by del z. And by definition this value is same as 1 by dv, that is the original volume, multiplied by the derivative with respect to time of change in volume. As far as the incompressible fluid is considered, the change in volume, that is delta V, is equal to 0, and therefore the volumetric dilation in the case of incompressible fluid is always 0. So we have volumetric dilation for incompressible fluid is always equal to 0. So in case of incompressible fluid, the total volumetric dilation, which is given as del u by del x plus del v by del y plus del w by del z, this sum must equal to 0. And we'll prove that this one is a law of conservation of mass in 3-dimensional, or number of times it is called as continuity equation or incompressible fluid and steady flow. The volumetric dilation is the same as the continuity equation, that is the law of conservation of mass we are using. And this term here is same as epsilon x, this term is epsilon y, and this term is epsilon z. That is, we have volumetric dilation. Del u by del x is same as epsilon x, del v by del y is same as epsilon y, del w by del z is same as epsilon z. But you have to represent this in a rate form, that is epsilon dot x, epsilon dot y, and epsilon dot z. In a standard notation, it is represented as 1 by v, the material derivative ddt of volume v, which is same as 1 by v into dv by dt, is same as epsilon dot x plus epsilon dot y plus epsilon dot z, and this value is equal to 0 for incompressible fluid. The rate of rotation or angular velocity. The rate of rotation, that is the angular velocity at a point, is defined as the average rotation rate of the initially perpendicular lines that intersect at that point. We know that omega is defined as the rate of change of angular displacement. So omega is given by d theta by dt, where theta is angular displacement in the time dt. In that case, we can define omega as d theta by dt. But in the case of fluid element that has the dimensions of delta x and delta y, and at origin we have the component along the x direction is u and y direction is v. Initially the angle between the line OA and OB is 90 degree. Now since here we have a variation of u along the x direction and the velocity v is varying along the y direction, In that case, this angular line OA will be turn in an anticlockwise sense, whereas the line OB may turn in a clockwise sense. In that case, they form an angle here. Let's say this angle equal to d alpha. Let's say this angle equal to d beta. Since here two edges are turned here, one is OA from OA to OA prime, OB to OB prime. So in such case, we have to consider the angular velocity about the z direction. So this axis is same as our x-axis. This one is y-axis. This plane is xy plane. So this element is going to rotate about the z-axis. So therefore, we are able to calculate omega z from the element that we have considered in xy plane. So this omega z was taken as the rotation omega z of the element about the z-axis is defined as the average angular velocity omega OA and omega OB of the two mutually perpendicular lines OA and OB. So this value of omega z is taken as the angular velocity of OA, that equal to omega OA plus omega OB, but in this case you have to take the average value, therefore you have to divide it by 2. And the sign convention follow is counterclockwise. The value of omega is taken as positive and clockwise was taken as negative. That is, this rotation is taken as positive value and this rotation is taken as negative value. So just now we have defined the value of omega, which is angular displacement by dt. So this time we have angular displacement d alpha. So that value will take as positive value because it's a counterclockwise. So it is d alpha by dt, and this value is a clockwise value. So that we have to take as negative is d beta by dt. So minus sign because rotation of OB is a clockwise, d beta by dt. You have to again take the half. So we got the value of omega A and we got the value of omega B, but you have to take the average value. So you have to multiply by 1 by 2. It means that to develop the expression for omega z, we must know what is the value of d alpha and what is the value of d beta. So we'll develop here equation for d alpha and d beta from the given element. On the line OB, we have velocity vector is v, and then on the vertical line passing through A, we have to write down the velocity vector in the form of v. That will be v plus we have del v by del x. Take out derivative of v with respect to x and you have cover a distance equal to delta x. Similarly, on the top edge, which is parallel to OA, we have a velocity is u along OA. So on the top edge, which is parallel to the x direction, the velocity is given as u plus. This time we have travel vertically upward, that is along the y direction. We'll take the gradient of u along the y direction. This time we'll multiply it by delta y. So using these two components, we can calculate what is the angular deformation here. So this edge is moving in the vertical direction with v. This edge is moving with a v plus del v by del x into delta x. So this angular deformation will be equal to, so in vertical direction we have difference is del v by del x into the distance traveled is delta x into the time delta t. So using this we can calculate d alpha. So if we take here the tan alpha, so we have tan of d alpha, which is basically a very small angle, so we can very well write d alpha also, is opposite upon adjacent distance. Opposite distance is same as del v by del x into dx into del t, and the adjacent distance is ox. So in this fashion we can use the definition of tan alpha and we can find out the value of d alpha. So divided by delta x. This one is same as delta x. It is divided by delta x. Delta x and delta x is cancelled, and we can calculate the term required, that is d alpha by dt. So d alpha by dt is same as this term. Here delta x and delta x is cancelled, is del v by del x. This time the d alpha is very small angle, and for small angle tan of d alpha is as good as d alpha. Almost similar way we can calculate the angle d beta here. This time we have difference in the velocity along the x direction is u, and this is u plus del u by del y into delta y. So the difference is here del u by del y into delta y into delta t. So we have tan of d beta. Again we have opposite distance by adjacent distance. So for small angle again we write this value equal to d beta. Opposite distance for d beta is del u by del y into delta y into delta t. Whole thing is divided by the adjacent distance is delta y. In this case delta y and delta y cancel, and again we can write d beta by dt equal to, here delta y is cancelled, this term is shifted to the left, is del u by del y. So we'll put this value back here in equation 1. We'll get omega z equal to 1 by 2 into d alpha by dt is del v by del x, and d beta by dt is del u by del y. So we have negative del u by del y. So this one is the expression for angular velocity about the z axis. So we'll just copy down this equation. We have x, y and z rotation like this one. So rotation about the x axis is represented by omega x, which is equal to again the 1 by 2 into del w by del y minus of del v by del z. And the rotation about the y axis is given as omega y, which is equal to 1 by 2 into partial derivative of u with respect to z minus partial derivative of w with respect to x. Now you can remember like this. So this frame representing our coordinate system x, y, z. Along the x we have component is u, along the y we have component is v, along the z we have component is w. So when we are taking the rotation about the z axis, then we have del v by del x minus del u by del y, this component. And if you take a rotation about the x axis, then we have omega x will be equal to del w by del y minus del v by del z. And if you rotate about the y axis, that is this axis, in that case we have del u by del z minus del w by del y. Even we have developed the equation that we have omega x equal to 1 by 2 del w by del y minus del v by del z, omega y equal to 1 by 2 del u by del z minus del w by del x, and omega z equal to 1 by 2 del v by del x minus del u by del y. So this total is an angular velocity vector and is written as omega bar, which is equal to omega xi plus omega yj plus omega zk. We can obtain here a curl, that is we have del cross v bar, and we'll equate the curl with 2 times of omega vector, that is we have 2 times of omega xi plus omega yj plus omega zk. 2 is common to all. Then we can very well write this equation in a vector form, and there is no need to remember any of this form. So whenever you have to solve any numerical and we require the value of omega x, omega y and omega z, just remember that we have a curl is equal to 2 times of omega. Solve the curl and equate with 2 times of omega, and we can successfully write down here the equation of omega x, omega y and omega z. To write the curl, I will select here I, then j, then k, then del is written as del del x, del del y, del del z, and we have 3 components of velocity are u, v and w. This value you have to equate with 2 times omega vector. So this curl you have to equate with 2 times of omega xi plus omega yj plus omega zk. Let's solve here the coefficient for I, and we'll equate this value. So for I, I will get del W by del Y. Second term is always negative, is del V by del Z. And if you compare from I here, I will get 2 times of omega x times I and I. So we can equate the value of omega x and we get the same equation here. So we have omega x equal to 1 by 2 into partial derivative of W with respect to Y minus we have del V by del Z. So this is a much better step as compared to the regular derivation. Now if you solve for j here, I will get here minus j. In that case I have to take the partial derivative of W with respect to x. So we have del W by del x minus we have partial derivative of u with respect to z. So we have del u by del z. And on the right hand side we have to equate with 2 times of omega yj. Only thing that this negative side will add inside, so these two terms will be swapped and we'll get omega y is equal to 1 by 2. So negative sign is adjusted, so I will write here first del u by del z minus del w by del x. Now check our equation for omega y is 1 by 2 del u by del z minus del w by del x. So absolutely there is no need to remember this. This equation is sufficient for you, that is the curl is equal to 2 times of omega bar, and you can comfortably write down omega x, omega y as well as omega z also. Let's check here k component. So for k component you have to take the partial derivative of v with respect to x. So we will get del v by del x. Second value we have minus term is del u by del y. And now this time equate with 2 times of omega z k. So we will get omega z will be equal to 1 by 2 is same as del v by del x minus del u by del y is same expression again, that is this equation. So best is to remember this equation and then solve this and compare it with I coefficient, j coefficient and k coefficient, and you can comfortably write down omega x, omega y, omega z. That is the curl you have to equate with 2 times of omega xi plus omega yj plus omega zk. That's it. The curl that I use here is basically called as vorticity and has a relation with rotationality. This vorticity vector is represented by zeta bar or sometimes is represented by omega bar, which is same as the curl. So this time we have vorticity, which is omega vector, is nothing but the curl, that is del cross v bar, and just now we have shown that del cross v bar is 2 times of omega vector. So from the given equation, that is we have vorticity which is equal to the curl is equal to 2 times of omega bar. So we can conclude here that the vorticity is a measure of the rotation of a fluid particle, and if the value of vorticity is equal to 0, it means that we have omega bar vector will be equal to 0i plus 0j plus 0k. That is, we don't have any rotation about the x-axis, y-axis and z-axis, will be called as irrotational flow. And if the omega vector is not equal to 0, any of the component is present here, so this time omega vector may be have omega x component, may have omega y component, or both component, or all component. In that case the flow is called as rotational flow. So this is the condition for rotational as well as irrotational flow. In addition to the vorticity, we will define one more term, that is a circulation. A circulation is a characteristic of a flow field, gives a measure of the average rate of rotation of a fluid particle that are situated in an area that is bounded by closed curve. So consider that we have a streamlines. So this is a one streamline. Tangent to it represent a velocity vector v. Then we have another streamline here. So all these are the streamlines. And in this streamline we will consider here a closed curve. So here we will consider a closed curve. and inside this closed area we are interested to know the average rate of rotation of a fluid particles, which is termed as a circulation. So streamline always give the direction of the tangential velocity. So this velocity at this point is the tangential velocity, that equal to v, and we'll consider here a small element, that is this element here, of length equal to dl. So to calculate the circulation, we have to take the path integral for the given curve along a differential segment dl, and to find out this value we have to dissolve the value of v along the perpendicular and the tangent to the path. Differential segment dl, this component is a tangential component which we represent as vl, and the other component will be normal to it, that you have to show perpendicular to it. So this one is a normal component perpendicular to the differential element dl. In this case the circulation, which is represented by the Greek letter gamma, is a cyclic integral because we have a closed path of the tangential component VL into dl. If this closed path is a circle, in that case you have to integrate the given integral over a circle. So instead of having a standard path here is a circle, the circulation gamma can be calculated as integral. So let's consider here that we have a circle here of radius equal to r as a closed path. So this time we have radius is equal to r, and let's say we have a angular velocity equal to omega. So we have omega is an angular velocity. So the tangential component in this case will be this direction here because I have taken the omega in an anti-clockwise sense. So this one is tangential component is VL, and this value of VL is same as omega multiplied by r, and the dl here is the elemental length here. So we'll integrate this term, that is the circulation. You will get the circulation equal to the cyclic integral of VL, that is omega into r, and this differential segment will show as a dl here, will make an angle equal to d theta and at a radius equal to r. So we can write dl as r multiplied by d theta. So instead of this dl we can write the term as r into d theta. Now since here r is a constant value because we have taken a circle of radius equal to r, and omega is a constant value that can be taken outside, so we have omega into r square. We have a cyclic integral that has to be performed from 0 to 2 pi. It means that we have completed a cycle multiplied by d theta. So if you solve this, you will get the circulation around a circular path will be equal to omega into r square into 2 pi minus 0. That is, we have circulation or a circular closed path will be equal to 2 pi into omega into r square. And there is a definite relation between the vorticity and circulation. The vorticity can be obtained from circulation also. So vorticity will be equal to the circulation divided by the area. So this time we have vorticity, which is represented by omega vector. Circulation is represented by gamma, which is equal to 2 pi omega into r square divided by pi r square. So we get the same term again, that we have vorticity is equal to pi is cancelled, r square is cancelled, we have left here with 2 omega. So this proves that we have vorticity is equal to 2 times of omega vector. And if you have to define technically the circulation, then the circulation is taken as a line integral of a tangential component of velocity about a closed path. The path must be closed, then only we can define the circulation. So the two quick term here, the circulation is given as a cyclic integral of tangential component multiplied by the differential elemental length, that equal to dl. If we have a circular path, in that case we have circulation is given as 2 pi times omega multiplied by r square, or simply omega multiplied by pi r square. Or you can remember vice versa, that circulation is nothing but vorticity multiplied by area, and vorticity is nothing but 2 times of omega. Area of the circle is equal to pi r square, So we have circulation is simply equal to vorticity multiplied by area. And we know that the vorticity is equal to 2 times of omega, and the area of this closed path is circle, that is multiplied by pi r square. And you can very quickly find out the circulation.